Morning, everyone, and welcome to the next installment of the JKMRC Friday Seminar Series that takes place here in Indopili, lecture theaters and online. My name is Karina, and myself and Katerina will take turns introducing the speakers this year as we co-share this Friday seminar. Before we start, on behalf of the University of Queensland and the Sustainable Mineral Institute, we'd like to respectfully acknowledge all traditional owners and the custodianship of the land on which we all meet today. We pay our respects to the ancestors and the descendants who continue cultural and spiritual connections to country. We recognize the valuable contributions to Australia and global society. Our speaker today is Dr. Mehdi Serati from the School of Civil Engineering here in the University of Queensland. Mehdi is lecturer in rock mechanics, deputy manager in the internationally recognized large open pit project since 2017, and an advanced Queensland Industry Research Fellow. The large open pit project aims to address critical gaps in the current understanding of rock slope failures and landslides in large open pits worldwide. Mehdi has over 15 years of teaching, research, and consulting experience in geotechnical engineering fields. His main research interest includes the design and setup of advanced experiments with pavements, brittle composites, ceramics, and superbly hard diamond composites. And today, the presentation is Tensile Fracturing in Brittle Solids. Please help me to welcome Dr. Mehdi Serati.
Wonderful. Thank you again for the invitation. It's an honor to be here with you and to talk to you about tensile fracturing in brittle rock-like solid. That's a topic that I'm very passionate about, and I've been involved over the last 10-15 years. So hopefully there is going to be something interesting in this topic for you today. Okay, so before we get the ball rolling, I would like to make a start with this famous quotation, which is attributed to Lord Kelvin, a mathematician, a physicist, and engineer who basically back in the early 1800s advanced the boundary of science quite remarkably. And it says, quote, "If you can't measure it, you can't improve it," which to me simply means that if you cannot it simply means you cannot manage what you don't know, and you don't know what you don't measure. So measurement is the basic, is the fundamental in engineering design. This chart here is also another illustration of the importance of measurement, basically in the geotechnical engineering field for the past 124 years or so. Back in the early 1900s, as you can see, the design of a structure installed on rock was heavily biased by engineering judgment and by mainly subject matter expert from previous projects, due to the lack of enough empirical data, and also not having enough standard recommendations. But over years now, we have advanced testing method both in the lab, in the field, and also advanced numerical simulation and probabilistic models. So the judgment is more, that we use in our design is more informed based on this, all this new technology becoming available to us. So measurements is the key. And when it comes to measuring properties of the rock, especially hard and stiff rock, measurements of the tensile strength is a very controversial topic. But why? Why is that? What is so unique about tensile strength measurements of rock, and why rock behaves so different, in my opinion, hard and stiff rocks when they are subjected to either direct or indirect tensile stresses? In order to answer the question, let's start with some basic. All right. So according to the International Society of Rock Mechanics, and I'm talking about the chart on the upper right corner of the screen. So the key property that distinguishes a hard rock from weak soil is basically an unconfined compressive strength of 100 MPa and above. So I'm talking about the pink zone on the far right corner, on the far right end of the spectrum. Between 25 to 100 MPa, if the unconfined compressive strength or UCS is within this range, it's basically classified as a medium strength rock. And anything below 1 MPa is not, generally speaking, classified in many literature as rock. Basically, we have a shared zone between extremely weak, highly fractured rock and very stiff soil. Hard and stiff rocks, like some of that you see on the listed for you on this table, they also have a very low tensile strength relatively compared to the compressive strength. They have a high stiffness or Young's modulus, which means high brittleness index, defined as the ratio of the compressive to tensile strength. In some cases, could reach up to 40, the ratio of UCS to sigma t. And the energy that you need to apply to deform the rock. If you put all these together, and especially if the rock is subject to cooling, it means that when tensile rupture happens, it's going to be sudden, it's going to be quick, it's going to be noisy, catastrophic, and very spontaneous. And I've got a few examples for you in the coming slide. All right, so this is a typical example of so that was a typical example of type of explosion, like hard rock explosion that you might have seen in the lab. This is also so here is also on the two clips on the right. You see the rupture of a sandstone, which is a relatively higher porosity. It's not as hard as a granite or basalt. You see that the formation of when you apply UCS at zero confinement. So all these photos that you see on the screen at zero confinement, and they are captured at around 100, 200,000 frames per second. So you see that when you're talking about sandstone, it's a formation of the crack is through an oblique shear plane. But when it comes to hard and brittle rock and a stiff rock like the one that you see on the clip to the left, it's very sudden. It's more like an explosion. It's totally different. It's absolutely different from behavior of a relatively less stiff and less strong type of sandstone rock. This is another example of rock burst or spalling, a type of hard rock explosion. This is not a blasting exercise, all right? So it's mainly a deep tunnel in hard rock due to higher stresses. So you can install seismic monitoring system, and so the operator recognizes that there is something happening and event is happening. So this is what we call which is commonly referred to as rock burst and spalling in the field. This is another example of this type of dynamic behavior. A big block of rock due to a spalling was separated from, as you saw, from the edge of the excavation and hit the support system. This one is interesting. It happens so quick, as you can see, again, rock burst is spalling. It happens so quick that the poor operator has no chance to escape the excavation area. All right, and what you see on the screen is our attempt to measure or understand spalling at the lab scale. So what we did, we have a block of rock, a cubic shape with up to, I think this case, different sizes, but from 100 to 200 mil. And there is a hole at the center, which represents the tunnel. And then, as you can see, when you applied loading, so under no confinement, it's a UCS, one principal stress in the vertical direction. The beauty is here at the roof of a tunnel, of the borehole, when you apply load, you get this tensile crack. You get the initiation and propagation of the tensile crack. And then at the side wall, when you have under this stress condition, you have the major, one of the tangential stress in compression. We see that the type of explosion and the fragments separated from the sidewall flying into the excavated area. It's very similar to the basic is very similar to the type of spalling or rock burst that we see in underground excavation. This is a work in progress, but one of the idea was to basically understand if you apply different confining pressure under biaxial stress. Yes, please.
What are the curves for that?
So these are the we recorded because it's so quick. We need to use a high-speed camera. So we use an ultra high-speed camera that you can run up to 1 million frames per second. This is what you see is the frequency of the camera. So what we did under different hole diameter, different biaxial loading ratio, we try to understand the spalling speed. So basically, you have the size of the fragment that you can collect after the test, and then we're using the high-speed camera calibrated. You can measure the speed, and it gives you the energy, the kinetic energy. So when there is an spalling happening as a function of the hole diameter and the ratio, what would be the energy release during a spalling? All right. So initiation and propagation of unwanted tensile crack is deemed to be responsible for spalling and rock burst, but it's not. But there are many other applications in rock mechanics that tensile fracturing in brittle solid is also very important and a dominant rupture mechanism, if you will. For instance, in hydraulic fracturing, this is an obvious case. We know, according to Kersh equation, in deep mine, when the ratio of horizontal to vertical stress is less than 30% or 1/3, then we get a tensile zone at the roof. This is very similar to the example that I showed you in the previous slide. And also more recently, relatively more recently, Kaiser and colleagues, they have also suggested that the spalling and brittle fracture in rock could also happen in weaker rock, like for instance, a slightly cemented sandstone or clay shapes. The image that you see on the screen is to give you an idea how extreme spalling incident could be. Imagine, so this is you are working in this environment, and these slabs or flakes, which could be very large, up to maybe 1 meter. It has sharp edges. The speed, well, it varies depending on the stress condition, but in our experiment could go all the way to 100 meters per second. Sharp edges, usually there is no fine or dust generated because fine or dust are mainly attributed to shear fracture. This is totally different. So it's a safety hazard, and if it's not controlled, it's going to be catastrophic and fatal. So, in a nutshell, tensile fracture in hard and brittle rock, if it's not understood properly, it could be spontaneous and catastrophic, it could be violent and fatal, and it could, most of the time, it lead to a large fragment with huge energy release. So, question, we need to find ways to measure tensile strength with ease and with reliable methods. So you might argue that we do have a standard recommendation to do that, right? But the problem is many of these standard recommendations, they have been developed when mines were not this deep, the depth that we are now excavating minerals. And as you go deep, you are confronting harder geological formation. Most of these old, maybe 50, 60 years old testing method to measure tensile strength of rock are very good when you are dealing with the medium strength rock. But when you apply it to hard rock, it is very difficult to follow the standard requirement entirely. And I'll give you some example in the coming slide. And most of the time, when they are adopted with hard and stiff rock, they tend to overestimate the tensile strength. And this is unfortunately a point that is largely ignored. Give you some example. The Brazilian test, which is you have a disc shape sample, you apply concentrated load, line load at the two ends of the diameter, and if you have the size of the geometry of the disc and the load at failure, you plug it into this beautiful yet elegant equation, and it gives you the induced tensile stress. But it is only valid, as you can see in this high-speed photography, it's only valid if the tensile crack happens or initiates at the center and propagates toward the contact area, and it forms a single tensile crack. All right. In an in a recent project, we tried to understand what happens if you get different fracture pattern, different tensile, different type of fracture mode, how it's going to impact our estimation of the tensile strength. So we prepared, that's a maybe 4 or 5 years project. So we prepared around 450, I guess, near 500 Brazilian samples from a wide different range of material. We had in our list, and here in this chart, you see the distribution of the Brazilian tensile strengths. We tested ceramic with up to around near 30 MPa of tensile strength, all the way to asphalt, which has only maybe less than 2 MPa of tensile strength. And in some cases, when we look at the high-speed recording, we need to use some specific filter, a technique to be able to record the initiation and propagation of the crack. And I think here is the fun and interesting part. When you test the Brazilian sample of a material, depending on its brittleness index, it's not only one, but you get 8 different type of fracture pattern. Type 1 and 2 are very similar, and this is what you expect from a standard Brazilian test, that you get a single crack, that single tensile crack that they split the sample into 2 halves, and it initiates from the center. Type 3 is when you have some moderate size type of shear fracture or conical shaped fracture at the contact area when the tensile crack is fully propagated. Type 4, which is very violent, it's when you have multiple cracking. Then we have type 5 and 6, when the crack doesn't start from the center, but rather start in a straight or concave or convex shape from one of the 2 contact area. This one is very interesting. We could observe it only in asphalt, and this is what you see here at the lower left corner of the screen. That was a transition from tensile to shear at some point during the crack propagation. As you can see here, for instance, and I'll try to illustrate it in this cartoon, is that you get the tensile crack at the center, and then it suddenly becomes a shear rupture, and we feel that it's related to the cementation and also the aggregate size. And the last one that we only observe with graphite. So no matter, by the way, in all these methods, we applied ISRM. So we did not play with the size, we did not play with the rate of loading. We always followed the ISRM recommendations in terms of the grains, like the size of the sample in 10 times larger than the grain size, and you know the standard requirement. But basically what this study suggests is that, especially for hard rock, like this is a PMMA, and I've got some other examples for ceramic that I also showed you in the previous slide, no matter how hard you try, as long as you are following the standard, there is no way that you can get that single crack. All right. Now, what happens then? So what issue could be raised? When we were testing, and well, the whole idea of this project really initiated when we were testing brick samples, and we had, like, let's say 20 different samples prepared. I gave it to different group of students, and each like 5 or 6 replications. And you're looking at the fracture at the final product. You get a beautiful single crack, all of them, but 80%, the force is also very similar. In 20% of this replication, the force is around 50% less. So the question was, how come you get exactly the same type of product, like the broken sample, but in some of them, the fracture, the force at failure is 50% less. That's why we use high-speed camera, and to our surprise, those samples that showed the lowest force at failure correspond to cases when the crack didn't start from the center, but rather start from one of the 2 ends, which suggests that although you may look at the sample, you are not implementing high-speed camera, you are not utilizing high-speed recording. You look at the sample, you break it, you get a single crack, it's all good, that's a tick. But the reality is how the crack is started, where the crack is started. It's not just the fracture, when and how the crack initiates make a big difference. In our study, it suggested could lead up to 40% overestimation if the initiation of the crack is not considered. The same applies for type 4. It means that in type 4, in some cases, and type 4 is here, multiple cracking. So if you test like your ceramic sample, you don't get a single crack, you use the Brazilian equation, you should expect up to 50% overestimation of the tensile strength. And that's huge, that's huge. So Brazilian test, if you are using Brazilian test to measure tensile strengths of hard and stiff rock, and getting a single crack is very difficult, you need to treat it with caution. Okay, I'm not trying to say it's invalid, because we did it in one of our journal paper and it was rejected because it said you need to be careful, people are doing. So you need to treat it with extreme caution. Now, what could be responsible? For instance, we are getting 8 different fracture patterns. How we can, what are causing it? Is it because of the boundary condition? Is it because of the, for instance, the grain size? What could be responsible for those type of fracture patterns? So in order to understand that, we develop a three-dimensional mathematical framework. We use double Fourier series technique when we implemented Popkovich-Norber coordinate independent potential. My apologies for this slide. I have no intention to go through these all equations, but just the reason that I put it up is just to demonstrate that this 3D framework, as long as we can introduce the boundary condition at contact using a double Fourier series, you can use the method to generate and get an idea about the induced stress inside the solid body. For instance, here we have the double Fourier series representation of case, a typical case that the load on contact is distributed uniformly, not only on the periphery, but also along the thickness, or different types of loading conditions. And I think this is the interesting part. All right, so in a standard Brazilian test, it is assumed the contact angle is small, less than 15 degrees. The load is distributed evenly on the contact arc length and also along the thickness. And if you use that testing or boundary condition, put it inside the three-dimensional framework, this is the red solid line is the type of stress distribution that you get when you are moving from A to B. So this is a tensile positive regime. It means that the maximum induced, and this is normalized based on the Brazilian equation. It suggests that the maximum tensile stress, which is in sigma XX, happens at the center. It's almost uniform all the way to 80% of the radius. That's why you get the Brazilian tensile rupture under a standard loading condition. What happens if the distribution of the load along the thickness of the sample is not uniform? What would happen if there is a violation of that? For instance, during the coring process, or there is a grain that has a different stiffness. What happens if you cannot safely assume that it's uniformly distributed along the thickness? The black lines are the stress induced from A to B in the horizontal direction for different ratio, different aspect ratio, or thickness to ratio, the thickness to radius ratio. In a Brazilian test, the ratio of the thickness to diameter is half. It means that thickness of the sample needs to be half the diameter. I'm talking about this guy here. So L over R is 0.5. If the distribution of load along the thickness is not uniform, look what's happened. The point with the highest tensile stress is not at the center no more, but it shifts towards the contact area, which is in good agreement with the experimental results. Because in the experimental result, you remember some of the fracturing didn't happen at the center, but it was rather at the contact. So with this 3D framework, we feel at least we can provide some explanation why the point of crack initiation is not at the center, it moves away from the center. With this result, one potential explanation is that when you are loading up the sample, when you're preparing the sample, the load at contact during along the thickness is not evenly distributed. All right. Okay. Now, here you see also some other examples of granite and basalt. Trying hard, there is no way you can get a single crack, and we already know if that's not the case, you tend to overestimate. What else we can do? So in an attempt with our colleague at UNSW, Hossein Nasumi, you may know him, we proposed that you can cut it half, the Brazilian test, cut it in half, and by carefully controlling the contact angle at this point, then you can get rid of all these unwanted multiple cracking and shear rupture, and you can generate a single beautiful single tensile crack. It means, and here you see also the numerical prediction that suggests that the point, the midpoint here, experience the highest induced tensile stress. It suggests if you can't fully comply with the standard recommendation for Brazilian tests because of the nature of the rock you are dealing with, you may, another alternative might be, you cut it in half, you load it up this way, you measure of course you need to have the geometry measured, you need to have this contact angle, and we prepare some specific spacer. You put it in that equation and it gives you an estimation of what would have been the induced tensile stress responsible for this tensile crack. We also try to challenge our 3D theoretical framework to understand the point load test. You don't need me to tell you, your expert knows better than me that the point load test is an index test. One way to do it, you have a cylindrical sample, you apply concentrated load using these conical contact points, and generally speaking, you get an estimate for UCS, but also we have an empirical equation that suggests you can use this empirical equation that I'm pointing to get an estimate for tensile strength. Using the theoretical framework, we propose this expression. It's purely mathematical, it's not experimental. And where you see in this chart, the prediction of this equation is plotted for you with the dashed line, one for Poisson ratio of 0 to get the spectrum, and one for Poisson ratio of 0.5. The dot points here is also experimental result. So hopefully you agree, given that it's an index test and you just need to get an estimation, there is no way that you do a point load test and get a very precise measurements of tensile strength. Hopefully you agree with me that there is a reasonable agreement between the prediction of this equation and the experimental results. By the way, you know that standard ISRM suggests that if you are doing point load test this way in a diametrical loading condition, the length of the sample needs to be always larger than the diameter. And it was always a question. Of course, we can test, you can try and see what it happens. And if you do it experimentally, you see that the results become independent of the sample aspect ratio if that standard requirement is met. You can try it experimentally. But what I like about this expression is that you see when the standard recommendation is met, like the thickness, which is 2L, is more than the diameter, you see that it becomes a plateau. So you can mathematically also prove that because of the way that the stresses are induced inside this 3D object, if that requirement is met, it becomes almost independent of that ratio. The ring test, again, those who are, if you have been using ring test, you know that if you apply a load on basically a Brazilian disc with a hole at the center, you get tensile crack from point M, which is the point with maximum tensile stress to N. But if you have done the ring test, and I'm quite sure that you are expert, you might have noticed that in some cases, depending on the diameter or the ratio of the hole to the diameter of the disc itself, not only you get this tensile crack, but also sometimes you get tensile crack in this direction. We didn't know what is contributing, but then again, using this theoretical framework, we could prove mathematically that if the ratio of the hole to the ratio of the hole to the diameter of the sample is beyond a critical point, there are always 4 points inside the diameter that reach the tensile strength of the material. Therefore, you get 4 tensile crack and not 2. If you're interested, we have explained it in this kind of now almost 6 years old conference paper. All right, my last type of experience that I've prepared for you is that, and I was involved, is that, well, brittle failure of rock is quite challenging and problematic, and getting the tensile strength of hard rock is also not easy based on what I demonstrated or what I've learned. But it's not only for rock or ceramic or hard rock, it's also with other type of super brittle materials like tungsten carbide and diamond. When working at the CSIRO on my PhD, I was fortunate to be involved in a so-called thermally stable diamond composite or a smart cut technology. Basically, what this does to cut hard rock, which has a UCS of more than 150, 200 MPa, there is no way that you can use mechanical cutting. You need to basically go drilling and blasting. But CSIRO patented the technology, is TSDC. If you Google it, you can find a lot of information that you can use these type of cutting elements to go and do cutting for extremely hard rock. And this is a type of setup that was available at the time. You see, for instance, we have a single cutter, which is a single groove. So we have a very strong rock, like say 200 MPa, and then you have the cutter here, and then you move it, and then you scratch the surface, and then observe the force and the development of wear on the cutting element. Very interesting result. It was not generated by me. I had access to this result. So what you see on the left is the development of wear flap on a typical tungsten carbide when it was used to like a line cut of a very strong rock with, I think, 200 MPa. Only after 1.3 kilometer of test, you can see the tip. Well, here is also obvious. You can see the WC tungsten carbide cutting element is completely blunt and it needs to be replaced. Okay, because of the huge thermal temperature generated at the tip of the cutting element. But look at the TSDC cutting element. Although this cutting bit, this cutting element has been used for 4.2 meter of cutting, which is almost 4 times the previous experiments, you see that the head or the tip is barely touched. So it means that it has a very superb wear resistance, very promising. The problem, though, and that's when I got involved in this project, is that you test the rock cutting with this new technology. Beautiful, everything is a tick. But then when you go to the lab, those TSDC cutting peaks suffer from premature tensile failure in the field. Why? And that's when I got involved. So I proposed that one potential reason, because we are measuring the tensile strength incorrectly, because we are using Brazilian test and there has been a debate. So I proposed that the value of the tensile strength that we get potential is incorrect. We need to find alternative method to get it right, and then we redesign it based on the new tensile strength. So again, I'm showing these results, but it doesn't mean that I was involved directly in all of them. I had access. So we test this type of TSDC cutting bits, which are mainly, at the time, it was available in bullet shape, as you can see, under different variation of load combination, compression, shear, tension. And then magic happens. So if you have a bullet test, and if you measure the contact force, you get you can get the tensile crack. It's very similar to the Brazilian test, but of course with the different geometry. So the question is, if you have the geometry and the load at failure, can you measure or can you calculate the tensile stress induced inside your sample responsible for the tensile fracture? I could not find anything in the literature for that type of loading condition and the sample profile could give us an equation for that tensile, the induced tensile stress. So what we did to replicate the test with different types of material, ceramic and graphite, very brittle graphite at different sizes, and I had to introduce the boundary condition in a prolate spherical coordinate system. And here is the result. This is an equation that we propose. If you're dealing with something like diamond, if you are dealing with a hard rock, you cut it with diamond. And now if you have diamond, how you want to cut it? It's very difficult. It's practically very challenging. But if you're dealing with such a material, and you know that the available testing methods are inadequate to get an estimate for the tensile strength, if you can manage to get a bullet shape and you measure the geometry and the force at failure, you can use this expression to measure the tensile strength. Guess what? Again, it was what I proposed, and the fantastic team that I've been working with. We use this method. We realized that yes, the tensile strength that you get for diamond composite was overestimated. So we redesign it, and again, when I say we, our group redesigned it, and then it survived tensile rupture, but then it suffered from shear failure because of changing the geometry. And it was to the end of my PhD. I really wanted to get involved and to improve it further, but I kind of disconnected. So basically, we proved that yet another method to measure the tensile strength is by loading a bullet-shaped sample, which might kind of seems odd because it's very difficult to prepare a rock this shape. It's not designed to rock this specific test, but rather to kind of very strong type of material like diamond that at the time we were dealing with during this smart cut project. All right, I've got 2 more slides, and I think we're good on time. All right, so when you have a rock sample and you apply confinement and confinement is high, we have beautiful, for instance, failure criteria like Moore, Coulomb, and Hotbrand that very nicely predict the ultimate strength. Okay, but when it comes to Spalling and rock burst, basically we are falling in this shaded area. And as you can see, Moore, Coulomb, and Hotbrand both overestimate the Spalling strength. So there has been quite a lot of advancement that you need to look at an S-shaped failure envelope, and there has been a lot of beautiful, nice paper, or a trilinear type of envelope. However, even if you look at these new papers, they largely ignore the importance of intermediate principal stress during a Spalling event. So we put a proposal, a discovery project proposal, with the same motivation that to understand the Spalling, especially in deep tunnels, and the available methods are inadequate, and mainly because of the exclusion of sigma 2 and temperature. And this is something that is happening. So it was successful. We are 1 year into the project. COVID has kind of delayed the progress, but hopefully we will learn more about this idea, and if opportunity arises, I might be able to share some of the results with you in another opportunity. For that project and for that Spalling strengths, we have access to this. Some of you may know this facility available at UQ Civil. So it's a true triaxial testing system, but it's a 4-in-1 kind of machine, because not only you can measure a true triaxial up to high stresses, up to under 85 tons, near 90 tons, on different sample sizes from 50 mil to 200. If you do the math on the 50 mil, you can go all the way to around 350 MPa to 320, which is enough to study most of hard rock. We can also measure, we can perform hydraulic fracturing, we can measure permeability, and we can measure behavior of rock at elevated temperature. Basically, if you have a material you're interested to develop a coupled thermohydromechanical constitutive model, I think this is the type of device is going to help you a lot. Here you see a concrete sample inside the cell under biaxial loading. Here you see a granite sample that there is a hole, and here we have a pack, a hydraulic packing. Basically, you plug it in, and as you are loading up the sample in 3 directions, different stresses, you can pressurize the hole up to 55 MPa, which is quite decent to understand the hydraulic fracturing behavior. And here, the grooves that you see at contact plates are where we are putting heating elements. So unlike some studies that you heat up the sample in an oven, you take it out, you load it up to understand how temperature impact the results. Here in this machine, we have the luxury of the heating element sitting right at the back of the contact plate. So as you're loading it up, you can manage the temperature. So it's a direct couple thermomechanical. And we have 4 PhD students working with the machine on different projects, and another lady who will hopefully join us soon in the coming months. All right, well, to conclude, mines, tunnels, you know, better than me, and excavation industry are basically going down. As you go down, the stress is increased, you confront harder geological formation, temperature becomes a problem. So it becomes a very difficult kind of environment, something that we may not have experienced in the past when we were like at shallower depths to extract minerals. We need to understand, and as you go deep, apart from many problems that could raise, the tensile fracturing in rock is also, and in the form of spalling and rock burst, is now becoming more commonplace in those type of environment. So we need to improve our understanding to avoid such catastrophic failure. We know that to understand and to avoid, to provide a better design for this harsh environment, the available models like Hook, Brown, or Morculum are inadequate. We need to develop new models. We need to develop new methods. Some of them are quite old, 60, 70 years old. And what I tried to present in this talk was some of the attempts that we have made to address the issue, but it's a work in progress. We are learning. And again, hopefully if another opportunity is given and we learn more in the future, I hope I would be able to share it with you again in the future. Thank you.
Thank you very much. Excellent presentation about tensile strength. We're going to open the floor for questions.
Thank you, Mehdi, for great presentation. I really enjoyed.
Thank you.
You mentioned that the location where that first crack appears is very important to estimate the tensile strength. And you said that you've done, when instead of full cylinder, you've done half cylinder and adjust the sample holder. You increase the chance of that first crack to come in the center. And you mentioned that it's important to have that sample holder adjust for the sample. If you do adjustment of the sample holder for the whole cylinder, whether that would improve the chance of having that first crack starting from the center or not?
It does, yeah. Basically, that sample holder, what I meant by that is the contact angle. Because depending on the type of the rock, if the contact angle is large than a critical value, which is a function of the rock type, we don't know, but it's a trial and error at this stage, you don't get a single crack no more. You get multiple crack, you get the shear at the contact, at the load discontinuity. There is no way that, so we try to improve it, but it doesn't work that way. So when I say sample holder, basically it's the contact angle, and you're absolutely right. Because depending on the value that you measure for the contact angle, you can eliminate the multiple fracturing. You get a single crack, which our studies suggest that always start from the center. Now, for that configuration, then you can use the geometry, you can use the angle, you can use the force to get what was the responsible induced tensile stress for that tensile crack. If it's not the case, if it's not tensile crack, then again, it's a very complex problem.
Thanks. And just one quick question. I mean, there's a lot of advanced new materials, kind of ceramic as well. Have you ever had a problem to break material that you're testing? And because it's stronger than the device you are testing in. Yeah. In the future, is there any problem? How are we going to measure those? tensile strength and compressive strength these real materials?
Yes, well, good question, because I remember for this ceramic we were using Maker, that's a brand name, Maker glass ceramic, and I remember we ordered from UK, we ordered like a UCS, and we couldn't manage to break it with any load frame available at UQ. Then we look at JK. You used to have a very, and I don't know if it's in operation back in old time when Eric was the lab manager. We could manage to break it, but then the thing is, it's a big system. How a stiffness is going to affect, because the sample, these type of huge machine and monostar are usually for big size, and this is a small. So absolutely right. When it comes to tensile, it's less important to tensile because sample is indirect tensile and it's induced, and you can adjust, you can play with the geometry to increase the stress concentration. But UCS, we had the problem. You're absolutely right. I don't have any comment, but potentially you can make the sample smaller, but then there is another question: how a scale is impacting the result. That's a good point.
And it's good. I remember seeing a lab that one of the labs used to love breaking the rocks and exploding them, and there was a banner on the wall that said "Go all the way." But just curious, how do you think you can apply this in a real case? It's a homogeneous type of samples, and it always seems that we underestimate any strength, whether it's tensile or whatever, because the heterogeneities that are inherent in the rock mass, right? And so that's why we use sort of brown or whatever to try and account for that. But how do you see, your work, particularly around the tensile and underestimation? Where do you see that being important in mining applications? How do you foresee it?
What wonderful question. So you may remember the results that I showed with Aspel, and there was a transition from tensile to shear. We don't know why it's happening. We know it's happening, we capture it, we document it, we don't know why. We are, with some colleagues, we're working on the numerical modeling of the problem to see maybe with numerical modeling, we might shed some light on that. So that's an example that heterogeneity and different aggregate size and aggregate type and the matrix, the cementation could play a role. This is an area that I'm also interested in. But when we talk about the spalling, because when you have a tunnel, and this is my understanding, is that of course within a tunnel, it happens in hard rock, it happens in low porosity, high crystalline rock, and it doesn't extend beyond at the maximum, depending on the spalling strength, the radius of the tunnel. So it's for this type of rock person, the spalling is shallow. It's close to the excavation boundary. So Holt Brown and rock mass take into account the discontinuity of strengths, and if you have the joints and so on. But for a spalling, because it's very concentrated on the boundary of the excavation up to a radius, I think for that range, it is a safe assumption that, and plus the size of the fragment, it could be a safe assumption that the discontinuities are not within that type of spalling is not making a contribution. Although a spalling and rock burst could also happen through a slip, so like a fault slip. That's a totally different scenario. I think it depends on the nature of the problem you are dealing with. Sometimes the heterogeneity and the anisotropy is critical, and this is an area I'm very interested to collaborate and learn more. But for a spalling, that's something we have been doing. I guess it's a safe assumption. So I would say for a spalling and rock burst, it's more the stress regime, like sigma 1, sigma 2, sigma 3, the ratio between them and the effect of temperature or couple processes would be far more important because it's very narrowed at that area, with less contribution of the relatively less contribution for the discontinuities or anisotropy within that shallow area of interest. That's my understanding.
Thanks for the presentation. My question is around manual go with underground openings, you have like in situ stresses plus hydrostatic stresses depending upon. How do you go about determining the hydrostatic stresses in addition to the in situ stresses at the lab scale? Because I could see that you have the principal stresses sigma 1 and sigma 3, but what about the hydrostatic stresses down there?
Hydrostatic, could you explain what you mean? Do you mean?
When you go down, so you have the water influence of water as well, that will be gushing into the rocks and all that. That will distribute to your principal stresses.
Yeah. Okay, so let me share some experience, and hopefully it will give an answer to you. Because we are also in a separate project, we are looking at fire-induced. This is a stress-driven type of spalling. We are also interested and been working for some time on fire-induced spalling in concrete and shotcrete. In a stress-driven type of spalling, it's a mechanically induced stresses that are far more critical. But when you go to fire-induced spalling, it's a pore pressure or thermal stresses. Mechanical stresses are also important, but these two becoming the dominant. My understanding is that you have pore pressure or excess pore pressure is important, but in the context, if you are dealing with shotcrete or concrete, especially during fire, my understanding is when you are looking at rock and hard rock, because it's usually happening crystalline, low porosity, at higher stresses. In my understanding and opinion, temperature and stress are far more important. Pore pressure might also make a difference, but we haven't studied that in mechanically driven spalling, because my understanding is that the contribution is much less. So we look at the factor of more importance, but nevertheless, it becomes a key, it plays a key role if you change the context. If you, instead of hard rock, low porosity hard rock, now you're testing concrete or shotcrete, especially under elevated high fire-induced temperature. I don't know if that answered your question, hopefully. But short answer to the question is, for hard rock spalling, my understanding is water has a less role compared to mechanically or thermally induced crack.
Right, thank you. I have just a question. Yeah. So it's more about the slope stability, and so when you are working in an open cut mine, and then you have stresses coming across at the base, right, and then this slope failure occurs. So in that case, your stress profile is entirely different, I guess, to what we determine using this lab scale test. So what are the tests at the lab scale basically to sort of simulate that kind of stresses? Because I know there are some modeling methods they're using, but any other like specific lab scale method that infer stresses at that scale?
Yeah, well, when you design the open pit mine, so basically we have a stress release because of the excavation, and then we have the D factor, which is the distribution of the damage beyond the slope. But I've always been interested in brittle fracturing. And brittle fracturing, and I've been working with Itasca, not directly involved in their project, but I've been being a member of the LOP. I've been access to the reports and have conversation with the lead researcher at Itasca. Those type of brittle fracturing in the open pit mine, although it open for research, but are very localized. So it's very localized. When you design an open pit mine, you basically are looking at the failure at the bench scale or inner ramp scale, or so those type of very localized that could happen at the crest or the edge could happen. It's not like that. It will not. It could happen, although that's a very shallow stress environment relatively. But it's very localized, and even if it happens, it's not going to jeopardize the operation. That's why it's mainly reserved for research. So I get back to your question, because I'm more interested in brittle fracturing. That has been of area, because it's very localized, it may or may not happen. I've never really been involved in detail, but you're right. I know that people, like at least in Itasca, I can put you in contact, are very much looking into those type of failure environment.
questions on that? No. Before I go to the online. Can your new CT ring impose temperature gradients, not just uniform temperature? And what are your thoughts about Spalling being related to thermally induced distress from temperature gradients? I think
Yeah, sort of address that. Yes.
Yeah, the thermally induced Spalling we have, I didn't show it to you, but we are working with our fire group and they have made quite an advancement in this area, and I'm fortunate to be working on 2 PhD projects together, one as the principal, one as the co-advisor. So you have this, so in the cell, all right, so inside the cell, you imagine you can go all the way to 200 mil. So imagine you have a 200 mil cube, which is quite decent, really. And then you drill a hole, and this hole could be across the thickness, or you may close the end, so it more generate the type of a tunneling environment. And then we have recently ordered, and we are in the calibration process, we have recently ordered a heating rod that can generate up to 1000 degrees. So you can use it as you have the block, you apply stresses in 5 directions because one end is free, and then depending on the stress regime that you're interested, and then you heat it up, the heating element up to 1000 degrees, you insert into the hole and you create a heat shock to see how the heat shock generates a spalling or failure, or you can put it inside, you heat it up, and in 15 minutes it reaches 1000 degrees. So there are different ways you can do it. This is again a project we have been working, but the early results suggest that again, if there is a fire in tunnel, it becomes a spalling, it becomes quite highlighted on the spalling of the shotcrete and concrete element. It's not about the rock. The rock itself is, again, especially if it's hard rock, it's if you go beyond the crack, the so-called crack initiation stress level, which is the onset of dilation. So the temperature, we have, there is this paper published by one of our students. Temperature does make a difference for hard rock, but when you compare with what happens in shotcrete, because the porosity is high and it's a different story, temperature is far more pronounced in a spalling of shotcrete and the concrete, at least the results that we have obtained so far. I don't know if that answers the question.
We have another question from Farhad. He says, good work, Mehdi. And we could assume distribution of macro fractures as well as characteristics of planes of weakness at grain scale might be the contributor to formation of cracks. It might be beneficial for the sake of research if you could characterize or visualize these macro fractures by scaling before testing. And he's interested to know your opinion about that.
No, that's absolutely true. We just, like 2 days ago, we submitted a $2.2 million LEAF project, a linkage infrastructure, whatever the acronym is, with my colleague and I'm not the lead here, I'm just fortunate to be part of the team. And it's a 4D dynamic CT scan, which I think the requested from ARC is around 1 million, and then another from the UK and contributing university. And that's exactly would enable those type of research that you put the sample inside the load frame, but it's very fast. The beauty is that it's different from other available CT scan, for instance, at UNSW, that you can do near real time relative to what is available in the market. So you can get an idea about the porosity, the grain size distribution, and as you load it up, you can see where the crack happens, micro cracks, leading to a coalescence of micro cracks to the type of that big fracture plane. So yes, of course, this is something I'm interested to know, and hopefully, if this proposal becoming available, we can learn more.
probably not a good time at 10:01 to ask another question. I know that Andre already asked it, and a couple of people brought up the heterogeneity thing, but it really was notable to me that all of the underground examples you showed were in extremely heterogeneous rocks, strong anisotropies. And I understand why you're starting with isotropic, high tensile strength rocks, but is it, and it's turned out to be very complicated. Is it, I'm just wondering how complicated, how possible will it be to ever develop the same sort of framework of knowledge for the majority of rocks that are extremely anisotropic?
Well, I'm not quite sure I would be able to give a clever answer to that, but to me is you needed all that information for design. Like for instance, crack initiation, which is a concept that's been developed by, for instance, Professor Derek Martin and Eric Eberhard from University of Alberta and British Columbia for years, and they have 20-25 years of research on that area. Peter Kaiser is leading that, so it's 20-25 years. And Spalling is complex, all right? And you cannot measure UCS or tensile strength and say this is related to a Spalling, but the onset of volumetric change or onset of dilation or crack initiation is the bare minimum. You need to make sure that the induced stress is always below. Now, that might, at some cases, might overestimate, but it's like that. If you want to add anisotropy, if you want to add temperature, whatever, it just makes the problem more complex. But then this is the bare minimum. You need to make sure that you don't go below. And I think one way is that's what we do. We simplify the problem. We're guilty as engineers to simplify the problem. But at the end, if you add that high level of complexity, you may get a more reliable estimate, but at the expense of a lot of time, a lot of research. While you could use a lower band that that's a bare minimum, which is crack initiation or similar concept crack initiation, which does the job for you for design, but with some extra in the expense of some extra factor of safety. So yes, you can spend this more time, more energy, more money. There are ways to improve that knowledge gap. But then the real question is, can we not use those simplified model for design? Does it work? It does work from research point of view, very valuable, but from a practical point of view, that's, I think, a point for debate.
Thank you very much, Mehdi. Next week, Sandra Rodriguez from the School of Earth and Environmental Science will hear from the review again. We'll present on hyperspectral characteristics of gold. We'll see you then. Please, let's thank you, Mehdi, Serati again.
Thank you again for the opportunity. I look forward to collaborate. I can see there are a lot of interest in this area, so hopefully soon we can work together on a similar topic. Look forward to it. Thank you.